Hello and welcome to Coffee with Caleffi. Today we've got an exciting topic. We've got returning champion guest host John Siegenthaler is going to be at the head of the class today. We're going to talk about hydronic cooling. This is an interesting topic that at Caleffi we've talked about for a really long time. The benefits of moving BTUs with water are well noted in the different hydronics journals and things that we've done over the years and all the Coffee with Caleffi presentations. But does it scale down well? So that's kind of what we're going to evaluate today with John Siegenthaler, and he's going to go through the slides and show you some ways to see if this is going to be a good fit for the next project that you're working on. So if you have any issues with the audio, best case is just to log out and log back in. That's probably the quickest way to do it. We will have a copy of today's presentation. If you want a PDF of that, just hit yes in the post-webinar survey. So you'll see a little box to check there. And then we'll put it up on YouTube. So if someone else in your office couldn't make it to the live version, or if you have to leave early, we'll get that archived and send that around in an email as well. And then this is a 90-minute presentation, so we have a certificate of attendance that we'll send to the attendees, and it's for 1.5 PDH, depending on your jurisdiction, obviously, so make sure that that works for their requirements. Then Hydronics 34 is the latest one to have hit all the bookshelves across North America. So if you did not get a copy of Hydronics 34, it's on the website. We've got the hydronics.caleffi.com version, which is kind of an interactive way to go through this. It's more like a long scroll magazine type digital version, or is just a PDF. But the hard copies were sent in the mail. So let us know if you aren't on the list and you would like to be. We can help you out there. And then next month, we get probably every other month a question about glycol, or like 10 questions about glycol, depending on the topic. So we figured we would have a glycol expert come on before the heating season and go through some of the key criteria here for how to select the right mix of glycol, how to keep it in good shape. So John's going to walk us through all those details. He's got a really good background in this world and will help us into the heating season with that topic. And without much further ado, I'm going to introduce John Siegenthaler. So he's going to cover the topic today. We'll be on the call as well to monitor questions. And then, yeah, thanks, John. Take it away.
Well, thanks, Max. We were talking earlier, it's kind of appropriate that we are, the topic today is hydronic cooling. I'm coming from upstate New York. It's closing in on 95, high humidity. First day of summer, and I'm sitting in an office cooled by a small scale hydronic system. So I guess all the stars lined up for this presentation. I do want to just mention a reference. Now we're going back several years here, but one of the issues of hydronics does a fairly deep dive into what I'll call smaller scale hydronic cooling. And that's available, as Max was saying, you can get this as a PDF. Right off the website. It's another good reference that will extend what we'll have time to talk about here today. So, small scale hydronic cooling, what is the rationale? Why should this be considered? Well, let's start with hydronics. You know, most people know hydronics is when it's been done properly, it has a good reputation for providing unsurpassed comfort, be it radiant floor heating or panel radiators or some other type of system. Properly executed hydronic heating does a really good job from a heating comfort standpoint. But over the decades, hydronics has primarily been understood as a heating technology. There's been very little application of hydronics in small buildings. And I mean primarily single family or small multifamily residential buildings, perhaps some light commercial buildings. Chill water cooling has been used for decades in larger projects where we have centrifugal chillers or large absorption chillers providing, you know, multi-hundred tons of cooling capacity and distributing that using water. But again, up to the present, it's been very limited in these smaller applications. So when we look at the hydronics market in general, we see that the lack of cooling, I refer to it as the Achilles heel of our North American hydronics market. And to some degree, this is true globally with hydronics. I've been involved in projects, and I'm sure many of you have been, where a client or a prospective client is quite excited about the prospect of hydronic heating, and that question comes up, well, what do I do about cooling? And sometimes the answer is, well, we don't do cooling, or here's a business card from my buddy, he does cooling, or just go out and buy a ductless mini split system. And oftentimes that involves multiple HVAC professionals, who's responsible for what. It can be very expensive and so forth. So it has been somewhat of a drag on the hydronics market for decades. And now with availability of hydronic heat pumps, and within that category, I've talked about water-to-water heat pumps that are typically tied to geothermal loops, or air-to-water heat pumps. And as you can see, air-to-water heat pumps is a rapidly evolving and growing sector of the market, and they'd be ideal. So whether, again, we're looking at air-to-water here and water-to-water over here, today all these units come with reversing valves. So when you buy either of these heat pumps primarily for space heating applications, you're also buying a chiller at no extra cost. The reversing valve is built in. And obviously, you don't have to use it in the cooling mode, but the infrastructure within the refrigeration portion of the heat pump is there. It's just a matter of making some electrical contacts, and you'll switch the machine from heating to cooling. And we also want to look at how the building market is evolving. One of the sites that I follow, Pro Builder, they have some interesting market statistics. What are consumers looking for? And I thought an interesting one was Generation Z. These are typically first-time home buyers. And what are they looking for in a building? And one statistic that was cited is that 80% of these Generation Z home buyers would not consider buying a home that does not have central cooling. And regardless of whether it's Generation Z or millennials or baby boomers like I am, most people today, especially in new home construction, are looking for cooling. 50 years ago, that wasn't as common. I grew up, like many people, without any type of central cooling. We turned on fans in the summer, but that market has changed. People have cooling oftentimes in their workplace. They have it in their cars. They're more or less going to expect it in their homes. So it is definitely a desirable characteristic of homes. And of course, with electrification growing, trends like net zero, bringing together hydronic distribution systems with heat pumps and offering a cooling option, it's an attractive market proposition. And as we go through the slides today, we're actually going to show a system towards the end that does space heating, cooling, domestic hot water heating, and also heat recovery ventilation. So it can tie all these HVAC functions together, excuse me, into a single system. So why consider chilled water rather than air side? Well, again, one of the very nice things about hydronics, water can carry almost 3,500 times as much heat per unit of volume compared to air. So the implication is that our conduits, if you will, the material we're going to send our heat transfer material through, water or air, when it's water, it's a much smaller conduit. And you can see here's a comparison based on typical cooling conditions. Chilled water in a 3/4 inch nominal tube size has got the equivalent cooling carrying ability of a 12 by 20 inch duct or an 18 inch diameter duct. And obviously it's going to be a lot easier to integrate that tube into a structure with minimal disruption of structure, minimal aesthetic compromises and so forth. Again, water, because of its high heat capacity and high density, we talk about distribution efficiency. How much energy, electrical energy, is required to move a given amount of either heating effect or cooling effect in a building. And I put down here 10x or more. A properly designed hydronic cooling system can use less than 1/10 of the electrical energy to distribute cooling through a building compared to an all air system. There's a variety of source equipment we're going to look at that can provide the chilled water. Zoning with a chilled water system is possible. It isn't something that always has to be done, but I'll compare and contrast single zone and multi-zone systems. Coil frosting, when you're working with a direct expansion coil, a coil that has refrigerant going through it, if the refrigerant charge gets low, it's possible to frost over the coil. Typically, when you see this, you know you've got a low refrigerant situation, or it could be something with the TXV and so forth. That's not going to happen with a hydronic coil. It simply doesn't get cold enough to cause that frost to happen. Low refrigerant volume. Again, this is just a graphic to illustrate when we're dealing with either a ductless mini split or commercially a VRF system, we're dealing with much, much greater volumes of refrigerant. Obviously that is a cost issue. It's also a safety issue if that refrigerant leaks and has to be replaced. And it's also a global warming issue. We don't want to vent or lose refrigerant. So a 4-ton heat pump, air to water heat pump, might have 6 to 7 pounds of refrigerant. An equivalent an equivalent ductless system, it could easily have 3 times that amount of refrigerant in it. There are some applications where when we provide or produce chilled water, the heat of rejection can be useful. We've designed systems over the years that provide chilled water for one purpose and also recover the heat from the condenser of the chiller and use that for a different purpose. And one example, we did a project for a facility that manufactured gelatin. And if you've ever made gelatin, you know you need chilled fluid or chilled water and ice to do it. So we're providing the chilled water with a water-to-water heat pump, and then we're recovering the heat on the condenser side and using that for domestic hot water in the building. So those are some really nice synergistic applications. And then finally, thermal storage. As we go into electrification, we're going to see utilities getting more creative with time of use rates, and water is an excellent material for thermal storage, both on the heating side, potentially on the cooling side as well. Now, I want to talk about distribution efficiency, just kind of give you a comparison. So I took some data for a geothermal water-to-air heat pump. And again, water-to-air meaning the water side is connected to a geothermal loop, and we're using some type of ducted forced air delivery system. In that particular unit, it was about a 4.5-ton rated unit. It had a 3/4 horsepower motor, and it was delivering about 1,500 CFM. And at full capacity, that motor was requiring about 690 watts of electrical input to deliver 53,000 BTUs per hour of cooling. And if you want to get the distribution efficiency over here, let me just move some things around so I can see it. We just take the rate of cooling delivery, 53,000 BTUs per hour, divide it by the power going in to operate the motor on the blower. In this case, it was based on manufacturer's literature, 690 watts. So we get this number. And interpreting this number, for each watt of electrical power fed to that blower, it's delivering, I'll round it off to about 77 BTUs per hour of cooling. Now let's compare that to a hydronic system. Let's say we're using a small circulator like this. It has a relatively low wire-to-water efficiency. It's not a great device as far as converting electricity at very high efficiencies into mechanical energy and imparting that to a fluid. So a typical PSC motor, about 22% wire-to-water efficiency. We could move that amount of cooling with about 77 watts of circulator input power. And I think there's a misprint there. Actually, here's the distribution efficiency over here. 53,000 divided by, I'll round it off to 72, about 737 BTUs per hour being delivered per watt. So in round numbers, we're at about 1/10 of the electrical energy requirement to move that fluid, liquid, water, as opposed to the equivalent cooling capacity being transported using air. And this is true on the heating side as well. It's really one of the underrepresented virtues of hydronic heating, the ability to move energy through a building on relatively low amounts of electricity. So what are some of the advantages of hydronic-based cooling? Well, let's talk about aesthetics. And, window shakers, I mean, you can drive around this time of year and certainly see buildings like this where you've got this type of through the window, through the wall air conditioning system set up. We've seen buildings with just dozens and dozens of these sticking out. The next step, I guess, would be a package terminal air conditioning system, PTAC units through the wall. I'm sure many of you have spent time in hotels, and oftentimes this is what you come into, basically a box that blows warm air, cool air into the room. I always tend to put a chair in front of one of these things just to kind of attenuate the draft a little bit. And then we move on to ductless mini splits, whether they're single head or multiple head units. You can see here's a 4-zone system. It's got 4 electrical harnesses. It's got 4 tube sets, so there's 8 tubes going out there. Oftentimes you'll see buildings with these concealment systems for the refrigeration tubing run all over the building. It works, but I think most of you would agree it's an aesthetic compromise on the building. Okay, rooftop units commonly used in commercial. Oftentimes you don't see them, especially on larger buildings. And then I had to throw a couple in that I've come across over the years. Exterior ducting down here. This is actually in upstate New York. It's a pretty cold climate, and this is actually used for heating and cooling. You can imagine the heat loss that occurs on this, or imagine this with maybe 3 feet of snow sitting on it. It's going to deteriorate over time. Here's one of my favorites. These are exterior air-to-air heat pumps. You can see the ducting going in the building, and you'll notice they're installed right under a metal roof. So again, this is actually up in the southern Adirondacks in New York State. That roof could easily have 2 or 3 feet of snow on it. And when that slides off of there, that doesn't bode well for the ducting or the heat pump. So, with a hydronic system, we can make much of this go away and improve the building aesthetics. Now, if you're going to design a cooling system of any sort, you do have to come up with a cooling load. And some of the folks today may not be familiar with this. So in simple terms, a cooling load is really, you can break it up into 2 divisions or 2 categories, sensible cooling and latent cooling. And the total load is the sum of these 2. Sensible cooling has to do with any kind of heat gain that really doesn't have moisture associated with it. So it could be conduction when it's 90 outside and 75 inside. You've got a temperature differential driving heat through the building envelope. You have sunlight through windows. If you have lights or other interior equipment, computers or anything like that running, all the wattage going into that interior equipment ultimately becomes sensible heat gain to the space. And a portion of the metabolic heat output of occupants also is contributing to the sensible cooling load. Latent cooling load is associated with anything that adds moisture to the air. So it could be moisture carried in by ventilation, air, moisture that leaks in, or I would say carried in by air that leaks into the building envelope. Certainly residential, you're cooking, you're taking showers, maybe you're washing the floors, anything like that. That moisture evaporates, that becomes part of the latent cooling load. And then occupants, respiration, perspiration, that contributes moisture into the space too. And for calculating these loads or estimating these loads, one of the most commonly accepted methods today is what's called manual J. And typically today it's done with software. And I just put a couple examples up there. There's Cool Calc that is based on manual J. You can Google that and get some information on it. RightSoft, RightJ has been around for years. It's been expanded over the years to the point where you can actually draw the building and it will automatically scale out walls and windows and so forth for you. And again, you're going to have to put in data as not only wall area, window area, and so forth, but also orientation. And the program is going to calculate things like solar heat gain through windows. That's a starting point. You have to identify or estimate what that load is before you start selecting equipment. Now, we want to do a couple poll questions today, and since we're talking about small scale chill water cooling, we want to find out, are you using it? So the choices here, I have no plans to use small scale chill water cooling, or I expect to design or install one of these in the near future. And the last one here, I already use this type of system. So we're just interested in what is the market size, what is the market acceptance on this. So Max is going to run that poll and we'll get the results shortly.
Yep, I've got that open, so the responses are starting to come in there. And yeah, we just had a couple questions as well. The one from Texas that they'd like to design hydronic cooling, but just kind of lack the team to do it down there between the MEP team and the HVAC trades to put it together. So hopefully we can provide some clarity with what John's going through today. But as mentioned, that Hydronics 13 is a good kind of background for that if you have the desire from one of those groups to get a little bit more into the details. And that's also kind of what we can help out with offline in kind of one-on-one meetings with anybody on the call if that's ever useful. So okay. I am going to go ahead and close this down. Okay, so I'll read these for you, John, in case you can't see it. So 16%, I have no plans to use them. 58%, I expect to design or install in the near future. And then 26%, I have already used this type of system.
Okay, that's good interest. Roughly a quarter of people have already used this type of system, and gosh, 58% that plan to use it in the near future. So that bodes well that this is a topic of interest. Okay, let's keep going here. Let's talk about chill water sources. We're going to focus a little bit more today on air-to-water heat pumps. We've done several past Coffee with Caleffi presentations dealing with the details. If you want more information on air-to-water heat pumps in general, Hydronics number 27 and number 30 would be good reference issues to look at. But an air-to-water heat pump system, as I mentioned earlier, it's a reversible refrigeration system, so it can provide chilled fluid. Now, the fluid is going to be a mixture of water and antifreeze in most applications in North America because we have to protect the system in the winter from freezing. And a common application would be where in the summer, the chill water comes into a diverter valve and it's directed into the coil of an air handler. And the blower draws air through the coil and provides dehumidification and sensible cooling, and then delivers that conditioned air through a ducted system. In the wintertime, the diverter valve would take the incoming heated fluid and direct it to some type of low temperature hydronic heating. It could be radiant panel heating, it could be panel rads, it could be a combination of heat emitters. But you can see it's a relatively simple approach. And geothermal water to water is another very viable chiller source for these small scale systems. I'm showing it here just going out to an air handler, but we could use the same detail with a diverter valve, and we could take the heated fluid in the wintertime from the water to water heat pump and direct that for space heating. So these are going to be probably the most common sources for the chill water. Now, what are some other possibilities? One is a deep lake water system. Again, I live near the Adirondacks in upstate New York. The water temperature 20 feet down is probably still in the high 40s. Very, very capable in terms of both dehumidification and sensible cooling. And the system up here is basically using some type of an intake that's supported up from the base of this lake. We don't want to be sucking in silt and dirt from the bottom of the lake. And we've got some kind of a pump that's pumping that in. This shows an automatic filter. These products are out there that can automatically detect when the filter media loads up, and then they can use domestic water pressure to basically flush themselves out. And of course, what we're doing is trying to protect the heat exchanger. We don't want crud in that heat exchanger. And then that water is returned back to the lake. It's a pretty simple idea. I would tell you as a very first step, check any environmental regulations before you think about this. Today, it's not simply a matter of dropping a pipe into a lake, even if you own the property and the shoreline. There may be procedures or qualifications to do that. Assuming that that is a hurdle you can cross, it's a viable system. Now, the other side of the heat exchanger, of course, that isolates the lake water from the balance of the system. It's just, in this case, it's a variable speed circulator, and it could be multiple air handlers, each with a zone valve. So as these zone valves open and close, the circulator would change speed, and you would trim out that system with air and dirt and magnetic particle separation. It has its own expansion tank. Basically, the left side of that heat exchanger is a closed loop system, whereas the right side is an open loop system back out to the lake. Now, another variation on this lake cooling is where instead of bringing lake water in directly, we're using some type of a lake plate heat exchanger. And there are a couple companies that make these. They've been used in the geothermal industry as a substitute for buried tubing. They are typically made of stainless steel, and I would describe them similar to some of the older style waffle plates that were used in solar collectors. Basically, it's two steel plates that are formed to create these dimples, and that basically causes the flow to spread out across the plate. And then it's welded together at the perimeter. And then multiple plates are manifolded into a header system. The header system would connect to typically high density polyethylene tubing, and that would come in. Now we're using a hydraulic separator. We don't need to separate from a purely technical standpoint. We don't need to separate the water that is in the closed heat exchanger in the lake from the water that's going to go out through our cooling terminal units. Now, again, I would check if you're going to use an antifreeze in a system like this. Again, be sure that any environmental restrictions are addressed before you look at these. And obviously, the number of situations that you could use either of these lake water cooling systems is going to be more limited compared to what's over on the left side there, air to water or water to water heat pumps. But all of these are potential sources of chilled water for a small scale system. Now we're going to look briefly again at air to water heat pumps. There's a lot of products on the market right now. Many of these products are known as monoblock air to water heat pumps, and what that means is that they come factory sealed with factory sealed refrigeration systems. There's no need to connect refrigerant line sets to these. The refrigerant is already in the machine. You're basically bringing out two pipes, running a mixture typically of water and antifreeze, and then bringing out the electrical harness to operate it. So these are relatively simple to install. Pretty much anybody that can do a hydronic system could set one of these units and pipe it, and the electrical is pretty straightforward. At the AHR show this past January, there was a major rollout of a lot of new products, and I walked the show and tried to take a few photos. The interesting thing is that you're seeing some of the major boiler companies like Weil-McLean, US Boiler, Viessmann, and so forth, getting involved with air to water heat pumps. They are reading the signs of the market where electrification is going to take the hydronics market, and they are providing these products. And some of these products are on the market right now. Some will be available later this year. But a major rollout year for air-to-water heat pumps. Many of these are also moving to some of the newer global warming, lower global warming potential refrigerants like R32 or R454B, the A2L refrigerants. They enable these heat pumps to go to slightly higher temperatures. Many of these can operate up to about 140 degrees. The coefficient of performance does drop when you push the machine up into those high temperatures, but they run a little bit, they're capable of running a little bit warmer than an R410 heat pump. So you can see, I actually made a list, and if I recall, there are about 19 different suppliers of air-to-water heat pumps currently on the market, or maybe I should say by the end of this year, having product available on the market. Another variation is what's called a hydrosplit system. This is basically when we're taking a monoblock outdoor unit and selling it along with an indoor unit. And the indoor unit would contain many of the products that would otherwise have to be individually selected and installed. Circulators, diverter valves, controls, expansion tanks, purging valves, and so forth. The box you see in the upper left there, that basically is, if you will, the indoor portion of the system in a box. And the piping is really reduced down to you're running 2 pipes out to your heating or cooling terminal system. You're running 2 pipes out to the heat pump. And in this case, you're running 2 more pipes to a indirect water heater. So manufacturers that provide this are trying to simplify and speed up the in-field work necessary or on-site work necessary to install one of these systems. A third variation is a split system. This is typical residential air conditioning where we have an outdoor unit, an indoor unit, and we have a refrigerant line set running between them. The outdoor unit typically comes with a refrigerant charge in it that's sufficient up to a certain number of feet of line set, but the installer does have to connect the line set, provide a pressure test, pull the vacuum on the line set, and then open the service valves in the outdoor unit and allow the refrigerant to go through the system. So contractors, installers working with a split system are going to require some skills and tools to work with refrigeration systems, and also an EPA 608 certification in order to buy refrigerant and so forth. So monoblocks, hydrosplits, basically plumbing and heating contractors that haven't necessarily worked with refrigeration systems can install those. I would still highly recommend they get the skills to eventually service those systems, to be able to add refrigerant or do other types of basic refrigeration service work on these systems. Performance. And this is typical. I mean, this is a graph for a specific product, but what you'll find with heat pumps and cooling capacity is the warmer it is outside and the colder you're trying to provide this chilled water, the lower the cooling capacity is going to be. So we're looking at curves here that all dive down as it gets warmer outside. And then when we look at leaving chill water temperatures, 45 degrees, we would be on this curve. If we can operate our cooling distribution system at higher chill water temperatures and still achieve proper cooling. And when I say that, I mean sensible cooling and moisture removal. We don't want to just cool air and not dehumidify it. We're not going to create comfortable conditions. But through sizing the coil in an air handler, it's possible to run systems at 50, even 55 degree chill water temperatures. And you can see that makes quite a difference in the cooling capacity of this particular unit. And it's really the same story with energy efficiency ratio, or in some cases, you'll see it stated as cooling COP. The higher the number, the better. So as it gets warmer outside, the energy efficiency ratio drops, and also it drops as we force that chill water temperature to go to lower and lower values. Okay. Now, geothermal. Again, water to water, several manufacturers that have water to water units that would be suitable for residential like commercial applications. This is a nominal 4-ton unit installed. You can see the piping there on the left. The two smaller pipes at the bottom actually go to a domestic water tank. It's a de-superheater. That would be these two pipes right here. So when this unit is operating in cooling, some of the heat coming off, the hot refrigerant coming off the compressor actually heats domestic hot water. So you're getting, under those conditions, you're getting free heat recovery. Heat that would otherwise be going out and be dissipated to the earth loop is instead going into your domestic hot water. And again, this is a whole sector of the heat pump industry, the science of doing the earth loops, whether it's vertical boreholes or horizontal earth loops. There's a lot of material out there. Hydronic's number 10 does address this to some degree, shows some applications for water-to-water heat pumps. And just a photo here, this was a project we did a few years ago. This is 2 5-ton water-to-water units. The piping has yet to be insulated there, but those units provide space heating and cooling for it's a Department of Environmental Conservation facility in upstate New York. And they also provide some domestic water preheating for that facility. And they are controlled on a 2-stage system, just like 2 boilers would be controlled. Water to water performance, it's the same concept as what we looked at for the cooling performance of air to water heat pumps. As the entering condenser water temperature. This would be the water coming back from the earth loop that is picking up heat at the heat pump and taking it back out to dissipate into the ground. You can see as that earth loop warms up over the course of the summer, or if the earth loop was undersized, we're starting to lose cooling capacity. And we also drop in cooling capacity as our entering source water. Now this would be the water coming back from the cooling coil in the building. As that temperature goes down, our cooling capacity goes down. So net effect is really the same as what we have with air to water heat pump. The numbers could be different, but the trending is the same. And it's also true with energy efficiency ratio. The warmer you can keep your chill water temperature and the cooler you can keep your earth loop, the higher the energy efficiency ratio, as well as the higher the cooling capacity of the water-to-water heat pump. Now, let's do another poll. What type of chiller do you use or perhaps expect to use for a small-scale chill water cooling system? And we've talked about water-to-water geothermal heat pumps. We've talked about air-to-water heat pumps. There are other types of chillers that are out there. There are some gas-fired absorption chillers, for example, or I don't plan to use this type of cooling. So Max, I'll have you run that poll, see what kind of spread we get here.
Okay, we've got that open. It looks like people are starting to vote there. One of the other questions that I'm getting in the chat as well, will this be archived? We will, and sometimes I have it up the same day, sometimes it's a day or so after the webinar. We'll have it on YouTube, so you can go back and refer to this. I'm also going to put just the whole playlist link in the chat too, so you can go back and see any of them that we've done over the last, since 2010, I think. We've got webinars in there, so the last 14, 15 years. So I am going to go ahead and close the poll here. And what we found is 15% air to water, geothermal, geo-exchange systems.
Water to water.
Oh, sorry, water to water. 77% air to water heat pumps, and then 5% some other source, and 3% I plan to use this type of cooling.
Okay. Wow. So air to water seems to be gaining a lot of popularity. So that's interesting and very useful information. So thank you folks for participating in the poll. Let's keep going. Now, small scale chill water cooling. Anytime you're handling chilled fluid, regardless of the scale of the system, there are different conditions that you have to respect compared to handling heated fluid. And since we're talking small scale buildings here, residential like commercial, many of the installations of hydronic heating don't insulate the piping. Sometimes code may force that if it's an unconditioned space or otherwise, but we've seen just dozens and dozens of hydronic systems where there's no insulation on the piping. That is a mistake when you're dealing with chilled water. And the issue is condensation on the piping, okay? So anytime that we have a tube, regardless of what it's made of, whether it's copper, steel, PEX, if the exterior surface temperature of that tube gets below the dew point of the surrounding air, you're going to form condensation. And just to give you some idea, yesterday here during our heat wave, we hit a dew point of 75 degrees Fahrenheit. So what does that mean? Any surface 75 degrees or cooler would have condensation forming on it. And this condensation will build up and eventually drip off the pipe. And if that pipe's over a ceiling tile or over a drywall ceiling, you're going to get a call back fairly quickly because it can make a mess in a hurry. So I always like to put this device up and ask what it is. And I'm sure some of you have seen these things. Maybe you played with one of these things in an HVAC lab years ago or whatever. This is called a sling psychrometer. And you'll see there's two thermometers, mercury thermometers that are in that main block. And then there's a handle over on the right. One of the thermometers has got a wick on the bulb. And the way you work this thing is you basically saturate that wick with water, and then you grab that handle and you literally spin the thing around for about 30 seconds. And as you do that, the water is evaporating from the wick. And after about 30 seconds, you read both thermometers. And the one with the wick on it gives you what is called the wet bulb temperature. If you've ever wondered where that term came from, this is where it came from, the wet bulb of a thermometer. And that temperature is going to be lower than what the other thermometer gives you, which is dry bulb temperature. And if you know the wet bulb and the dry bulb temperature, you can calculate what the relative humidity is. In fact, you can calculate a lot of things from knowing those two temperatures using a psychrometric chart. This is not a psychrometric chart, but it is a relationship between dew point temperature that you would read from the wet bulb and the dry bulb temperature. If you have a certain combination, for example, here it shows a dry bulb of 75 and a wet bulb of about 55, and that corresponds to that red line. And if you follow it up, about 50% relative humidity. So again, knowing wet bulb, dry bulb temperature, you can determine relative humidity. And I'm sure there's multiple softwares out there that would do this for you without needing the graph. I wanted to show you what can happen in hydronic systems carrying chilled water that don't have insulated components. Pump volutes in particular, from what I have seen, are quite prone to oxidation. Now, these pumps are all still operating, they're operating fine, but you can see, especially this one here in the middle, this is actually only 2 seasons of chilled water cooling, and that's in upstate New York. That we don't run that cooling, from May to October. It might be just 2 months of cooling. You can see the piping next to the pump or the circulator is insulated, but you can see the surface oxidation, not only pump volute, but you can see the steel hardware on the isolation flanges here. This is zinc plated hardware that's also corroded, and you can see where the condensate has dripped and eventually dripped down on top of something else in the system. This circulator seems to resist a little bit better, but you can also see the flanges and the steel pipes here. Here's another one. This is plastic pipe, PVC or CPVC pipe. And again, you can see the surface condensation that is formed. So you have to do chill water piping insulation properly. If you can't commit to that, I would tell you not to get involved with chilled water cooling systems, because not only aesthetically does this create problems, but just the dripping water can really create some major, over time, structural, mold, aesthetic problems in the building. So how do you deal with it? Well, typically in these small systems, elastomeric foam is probably the most commonly used insulation. It's readily available. When you use it, it's important that the seams are glued together properly, as well as the butt joints. There are companies that sell pre-insulated PEX. We have used this on projects. It's really nice. You can run this from basically a basement mechanical room up to an air handler without having to piece together all the individual 6-foot pieces of elastomeric foam. It's available from 1/2 inch all the way up to 2 inch. There are other materials like foil wrap fiberglass. What you don't want to do is put a material on here that lacks a vapor barrier. The vapor migration will be from the outside towards the pipe, and if that was just the fiberglass material, it's going to get saturated very quickly with condensate. The photo down here actually shows some of that pre-insulated PEX. You'll see some 1/2 inch PEX, aluminum PEX up here. This actually goes out to panel radiators for heating. But the 2 pieces of pre-insulated PEX, they're supported on nylon straps. And as I mentioned, these go right from a basement mechanical room right up to an air handler. And there are PVC shells that you can get as well. Typically, when you get into commercial installations, you'll see some nicer insulation systems. They are expensive and they are labor intensive. So typically on the smaller systems, the elastomeric foam is probably the most cost effective and one of the easier products to install. You can get it in sheets, you can get it in tube lengths, or, as I say, pre-insulated tubing. It is critically important that you seal the joints up. Here's a plate heat exchanger that's been wrapped in a sheet. This is 1/2 inch thick sheet, and it's been glued together with contact cement. The entire heat exchanger, and eventually all this piping will be insulated as well. So again, you really can't cheat, so to speak, when you're doing chilled water insulation, chilled water piping insulation. I tend to like miter cuts for things like T's and elbows. You can, one of the tools, interestingly, we find that an electric carving knife is one of the easiest tools to work with this material. A utility knife, it really it's kind of frustrating to cut this material with a utility knife and expect to get nice clean joints. With an electric carving knife, you can actually cut a really nice miter. You can set up a simple wooden miter box and cut these angles accurately, and then typically use a rubber cement or a rubber-based contact cement to bond these surfaces together. So take the time to do it right. Make sure you insulate not only the piping, but as I say, the circulator volutes, as well as valves, air separators. Some components are available. I know Caleffi sells some components with insulation shells. Some manufacturers also have, over here on the right, here's a circulator from Grundfos that has an insulation shell available. It is important when you use these shell products that you seal the seams up. Remember, if air can move and get in contact with that surface, whatever it is, whether it's a valve or a circulator volute or a pipe, you're going to have condensation. So when you put this together, make sure you use some type of a sealant, probably silicone, caulk would be good. If you're wondering how much insulation do you need, for most applications, 3/8 to 1/2 inch elastomeric foam is adequate. If you're into like a tropical situation, 90-degree temperatures, 80% relative humidity, and you're dealing with, some these different pipe sizes here, nominal pipe sizes, manufacturers are recommending 1 inch thickness. When you support piping that is going to be insulated, again, we've done systems, I'll admit, we've done systems where we've had stirrup hangers, and what will happen with elastomeric foam quite quickly actually is the foam will sag. under the weight of the pipe. This is a clip from HoldRite, and I've used a number of these over the years, and they work very well. It's just a plastic clip that goes into a strut channel. And if you look carefully at it, you see there's a couple, there's little ribs inside this that actually mechanically support the weight of the pipe, but they also allow the insulation to slide right into both ends of this fixture. And then it doesn't show it here, but it beat a silicone caulk around the outside. And now you've got a nice complete vapor barrier and a properly supported pipe that won't sag over time. So there are perhaps other products out there, but we found these to be very useful for this application. Here's another photo. This it does show, quite honestly, sometimes insulating some of these piping components where you've got some type of anti-vibration separator here. You've got valves involved. You can see the insulation. This is elastomeric foam. It's been wrapped around there. Foam tape has been used to put it together and so forth. Again, it's a necessary part of dealing with chill water piping, and it's very important to do it correctly. One final photo up here, zone valves. Don't insulate the motors. That also applies with circulators. The volute should be insulated, but make sure you leave the actuator or the motor of a circulator uninsulated because it has to dissipate heat, especially if it's also being used in a heating mode operation. All right, let's talk about terminal units, specifically air handlers. And let's see. In small scale systems, there are a variety of air handlers available. They're usually categorized as either horizontal or vertical. There are some products on the market now that can convert between vertical or horizontal, depending on what the application is. Basically, it would change the orientation of the coil inside the cabinet. But generically, you have a coil, you have a drip pan, which is very important. Make sure that if you're working with air handlers and chilled water, that there is a drip pan that would catch the condensate that's going to form on that coil. A blower, many of these systems today use ECM motors in the blowers, so the power input is lower, okay? And you can see a connection up here for a supply duct. This is what I refer to as a high static pressure unit. This is designed to work with a trunk that eventually splits up into several small 2-inch diameter flexible ducts, and very well suited to retrofit applications, in particular because of the ease of running that flexible ducting through framing cavities. Here is a horizontal air handler installed. It's actually sitting on a secondary drain pan. The secondary drain pan is there to catch anything that might leak through the bottom of that unit. Over time, that primary drain pan could corrode and simply fail, and you start to get a leak. And if that air handler is installed over finished ceilings, for example, as is the case here, we don't want that condensate dripping down on that ceiling. So it's just a plastic pan that also has a drain connection to it. Here's return air, supply air plenum. Here's a disconnect. Here are the two pre-insulated, this is 3/4 inch pre-insulated PEX that go to the coil, okay? And down here you see the trap. The trap is needed, especially if you're going to take this condensate to any kind of DWV piping system. You don't want any type of sewer gas coming back out, and that piping needs to be pitched. Sometimes this runs outside. Sometimes it does run to could be a vent pipe in a system. Try to avoid it going directly into soil pipes and so forth. And then once a year, when you take a look at this unit, make sure that you run the brush through that condensate trap. It's going to get some algae, and again, I'm not a biologist, so I'm not sure if algae is the correct term, but you're going to get some slime that just builds up in that trap. And most of these traps are supplied with a small brush, and you just pop the cap off and you run the brush through there a few times and clean it out. Some of them also come with a switch, and that switch is going to be tied into the low voltage control system for that air handler. And the purpose of the switch is if the water level in the trap rises, let's say we have a blockage either in the trap or in the piping taking that condensate away, that switch can actually open and it can prevent the air handler from operating. And the idea is we don't want the air handler operating, producing more condensate, only to have that condensate overflow the trap or otherwise leak out of the unit. Over here on the right, we've got this is an air handler, B&D manufacturing. Kind of an interesting product. It's roughly about a 2-foot cube. So it's 2 foot high, 2 foot wide, 2 foot deep. And they can configure the airflow in a lot of different directions, either straight through it or through at an angle, so forth. You see this is just return air coming down to a side connection here. There is a filter in here, and there's a nice large multi-pass coil for chilled fluid. You see the piping here. The circulator volute hasn't been insulated yet, but the piping is insulated, and then supply air comes out the top of the air handler in this case. Okay. So again, there's several companies out there that make these in different configurations. Again, just a close-up of the trap. Here's the brush that comes with it. Here's the clean out caps. Sometimes there are 2 of them. I do recommend that you order them with that emergency switch so that you can prevent that air handler from operating if you get a blockage in that drainage system. Now, rating data on air handlers. I don't want to go into great detail, but there are quite a few different ratings here, both sensible cooling capacity, total cooling capacity. If you want latent cooling capacity, it isn't listed, but if you subtract sensible from total, you'll get latent. This shows different entering water temperatures. The colder the entering water, the higher the cooling capacity, the numbers that you see down here. Different fluids, different flow rates. The higher the flow rate going through the coil, the higher the cooling capacity is going to be. So it's a typical rating sheet. And after you've done the cooling load calculations and you're, you know what your sensible and latent cooling loads in a given space are, you can start to look at data like this and select a unit that has approximately the same capacity. Now, multi-zone. We can also distribute chilled fluid, whether it's water, mixture of water and antifreeze. We can go to several different types of zoned heat or cooling terminal units, rather. Meissen makes some fan coils. They do have drip pans in them. They have the tangential blowers. This is actually the unit I have in my office. It looks like a ductless mini split, and it operates exactly the same way with a remote control. You see there's louvers down here that will open when it's operating. The only difference is this has a hydronic coil rather than a refrigerant coil. Yaga also makes some nice units that can be either recess mounted or surface mounted. Mestec has some fan coil units. So they're available out there. And again, I stress, you definitely want to make sure the unit is supplied with a condensate collection pan, and if so, it would have a drain connection. Similar rating data that we just talked about, total and sensible cooling capacity, different entering air conditions. In this case, it shows 45-degree entering water temperature. Typically, you'll find tables for other entering water temperatures or correction factors so that you can match the cooling capacity reasonably close to what your cooling load calculation is. Now, here's a pipe setup that is generic, but it shows what would be necessary for, let's say, a 4-zone cooling system using some type of air handler. I'm showing a wall-mounted console. Typically, there'd be a remote that would turn it on and turn it off. You're going to have to bring wiring from that unit, and typically it's going to be low voltage wiring, but you have to coordinate the operation of that unit with the balance of the system. And So you're going to need low voltage cabling coming back to some type of zone controller. You're going to need supply and return for the coil. You also need condensate drainage, and you need line voltage to power the blower. So you can see what I'll call the infrastructure needed to each of these fan coil units is substantial. So again, insulated supply and return piping, line voltage and low voltage wiring, condensate drainage, a zone valve, okay? And one of the things I want you to keep in mind when you do these, and this is actually turning into somewhat of an industry given all the ductless mini split units that are out there, is cleaning. These coils and the inside of these units, when they're operating, depending on the climate and quite honestly, the cleanliness of the space they're in, they're going to have some mold form. They're going to have some deposits on the coil. And there are some companies, there's actually one called WeCleanHeatPumps.com if you want to check them out. And what they do is they put a clear plastic bag onto this unit, and basically it's a catch basin. They have a frame that holds it. And then they use a small electrically powered power washer with some type of a detergent and basically spray down that coil and then allow that material that's been sprayed to drain into this bag. So again, I want you to think about doing this on an annual basis. If you have 4 or 5 of these heads in there, it might be in a living room, over the sofa, over the piano. You know, logistically, this is kind of an imposition on the occupants to come in and set up this. It's all doable, but it's something that should be considered as an alternative. You might want to consider a single zone cooling as opposed to a multi-zone cooling. And really, I would tell people, if you're looking at multi-zone cooling, I really want to hear, how are you going to use it and why do you want multi-zones? You know, if it's, I want to keep this room at 75, I want to keep that room at 76, and I want to keep another room at 72, I'm going to try to talk you out of multi-zone cooling. You know, if you have a very large building, yeah, multi-zone cooling is probably reasonable. But in a typical 2,000, 2,500 square foot house, my experience has been typically in the summer, when the cooling system is on, you're cooling the whole building. You might have some airside dampers to do some zoning. And that, quite honestly, would be easier than dealing with all the infrastructure that you need for multi-zone cooling. Okay, and also, depending on the heat pump, you might have to use a buffer tank, simply because these units might be in the range of 3/4, 1, maybe 1.5 tons capacity at the most. If you've got a single speed 4-ton heat pump, you know, you're going to get into a short cycling problem without a buffer tank. Now, the inverter heat pumps, different story to some extent, although again, extensive zoning could still require a small buffer tank. Here's another interesting approach. There's a company up in Canada called Thermatlantic, and what they're doing is basically they're putting a coil into a container, a sheet metal box, but there's no blower in it. Okay, there is a condensate drip pan, so essentially they're bringing the chilled fluid up to the coil, collecting the condensate, and then they're using these individually controlled axial fans. These are quiet, they're quite efficient. And you can see what they're doing here. They're taking insulated flex duct from the connections on this unit. And each of those flex ducts contains a fan. And the operation of that fan is coordinated with a zone thermostat. So in this case, you've got 4 zones of cooling, but you're doing the zoning on the air side as opposed to doing it on the hydronic side. Certainly, if you're going to use this approach, you want to make sure you have access to all these fans. You don't want to bury them under ceiling insulation or bury them in some inaccessible cavity, because at some point you may have to service them. I thought that was a pretty interesting approach, though. You can check them out again at thermatlantic.com. Now, I tend to like single zone cooling combined with multi-zone heating. So again, here's some examples of air handlers. These are whole house air handlers. This one is installed in a house that has spray foam up against the underside of the roof deck. So that entire space is within the thermal envelope of the building, which is nice from the standpoint of running ducting and minimizing losses. So the advantages of single zone cooling greatly reduces the insulated supply and return piping, as well as condensate drains, wiring, and so forth. You only have one coil and one filter to service. So you have a single point of service as opposed to going around and spraying down each one of these wall-mounted units. Okay, you can locate the air handler out of sight, but accessible. Okay, and you don't typically need a buffer tank in a cooling mode. If you're matching the coil capacity in your air handler reasonably well to the cooling capacity of the heat pump. Don't put a 2-ton air handler on a 5-ton heat pump. You're simply going to short cycle it. But the trending, especially today with both air to water and water to water heat pumps, is inverter compressors. And the nice thing about that is the machine, the heat pump, can actually adjust its compressor speed based on maintaining a certain leaving water temperature. So now you can actually have a heat pump that can reduce its cooling capacity and match a smaller air handler. Okay. The other nice thing about that is that since if we don't need a buffer tank in cooling, we can use a buffer tank or a reverse indirect water heater, and we can provide both cooling and domestic hot water heating in summer. Now, we can't do both at the same time. We have to toggle back and forth, and we'll get into some slides on that. So, here's an example of multi-zone heating where we've got panel rads and we've got some floor heating circuits, and we've got a single circulator, a variable speed circulator down here that handles all that. So we can do extensive zoning on the heating side and still combine it with single zone forced air distribution on the cooling side. Again, a schematic. This happens to show a split system air to water heat pump. You can see here we got a diverter valve. So in heating mode, we would direct our flow over into our tank. In cooling mode, we're coming down through the air handler. And notice the buffer tank is not involved in cooling mode at all. So this tank can be maintained at some elevated temperature in the summer to either preheat or fully heat domestic hot water. And your control system, and some heat pumps today actually have these controls built in, you can determine which is the priority load. If you have a simultaneous call for cooling and domestic water heating, one of them has to take priority. And often it's just a dip switch or a software setting that allows you to pick which one of those you want. This tank has internal coils. It's a reverse indirect, so it is basically cold domestic water comes in, it goes up through the tank's maintained at temperature, and it might be 110, 120 degrees. So you could get a substantial, perhaps even all of the temperature lift required for domestic hot water. I'm showing an electric tankless water heater as a booster, simply because if you're controlling this tank temperature on outdoor reset in the winter, the tank might be at 85 or 90 degrees on a mild day, and that's not warm enough to fully heat the domestic hot water. So we need some kind of a booster. It could also be a small, like a 30-gallon tank type heater. And we've got a variable speed pressure regulated circulator, and then again, a manifold, home run circuits going out to whatever, panel rads, towel warmers, floor heating circuits. All of these can be controlled based on thermostatic valves. So it's a nice combination: space heating, space cooling, and domestic hot water. System design concepts. Okay. Now, single speed heat pumps. Cooling capacity on the coil, you have to match the coil to the cooling capacity. I'll say the nominal cooling capacity of the heat pump. Again, we don't want to put a 5-ton or even a 4-ton heat pump on a 2-ton air handler. You're simply going to be cycling the heat pump on and off quite a bit. So a buffer tank could be used. Good news is many of the current generation, air to water, as well as an increasing percentage of water to water heat pumps are going to use inverter compressors, variable speed compressors. So when we do that, at least my opinion on that, since the heat pump can control its capacity based on maintaining some set chilled water temperature, you don't need to go into the buffer tank to do cooling. So again, we're coming out to a diverter valve, and we're simply going down through our coil, coming back to our heat pump. When we switch over to either space heating, or even in the summer, we switch to maintaining some temperature in this tank, our diverter valve simply sends it up through, and we could even have, I'm showing an electric boiler here as backup. If the heat pump is down for some reason, this is at least going to provide space heating and domestic water heating. So I put down here, cooling is generally selected as priority over domestic hot water, especially if there's an auxiliary domestic water heater. So if we had a, let's say a 30-gallon tank as our booster, based on using these coils as a preheat, that tank could provide domestic hot water on its own, it can cover the domestic hot water load. For example, if somebody's taking a shower while the building is being cooled. So in those circumstances, cooling could be selected as the priority load. You may go the other way, but keep in mind, you can't do both at the same time with a single heat pump. When we get into multiple heat pump systems, there are much more complicated approaches, but they would be capable of simultaneous heating and cooling. All right, now let's talk about this. Here's that same schematic. Now, one of the little nuances of switching between cooling and, let's say, domestic hot water heating, when we shut off in domestic water heating mode and we resume cooling, you want to think about the fluid that's in the heat pump as well as in the piping from the heat pump into the mechanical room. That fluid could be 120, 130 degrees, depending on what that tank temperature was. If we just move the reverse or the motorized valve and we send, let's say, 3 or 4 gallons of 120 degree fluid into the cooling coil, imagine you're sitting there in a living room and it's a hot, sweltering day. And when the cooling comes back on, you get this blast of warm air for maybe a minute. Most people are not going to like that. They're going to say, why is the system blowing this, this slug of warm water, several times a day when cooling comes back on? So how do you deal with that? Well, there's different approaches, but one approach that is kind of interesting, instead of using a 3-way motorized valve, you can use two-way motorized valves in combination with a differential pressure bypass valve. And the way this works is during a mode switch between, let's say, cooling to domestic water heating, both of these valves stay closed. And the flow basically goes through the differential bypass valve and goes right back out to the heat pump. So the only fluid that the heat pump is actually working on at that time is a small amount of fluid in this loop right here. So it's going to change its temperature quickly. If it was 120 degree fluid and the heat pump comes back on in cooling, literally probably in less than a minute, it's going to have that fluid down to a temperature at which you can then open this valve and allow that chilled fluid to go up through the coil and not create that slug of hot air that you would get if you simply switch with a 3-way valve. And same thing occurs when we're going from cooling into domestic water heating. We have cool fluid in this piping. This valve would be shut. The heat pump would operate in heating. It would rapidly heat the fluid here. Then this valve would open and the fluid would go over to the buffer tank. I put together some relay logic. Time delay relay is making the decision on when this can happen. You could also use temperature sensing to make the decision. And I do want to point out that some heat pumps that are out there have this logic built in. They have this transition logic so they don't end up sending hot slugs into a cooling coil or cool slugs into a buffer tank or some other load that is expecting hot fluid. So that's something you want to address as you design a system. Now let's run through a few example systems, and let me just check on time here. We should have a little time for questions. Here's a system, a monoblock heat pump, three-way valve. We're going to a reverse indirect, or we're going to a cooling coil. We're using this for preheating domestic water. I'm showing a small tank type water heater as a booster. Variable speed, pressure regulated circulator going out to a manifold. And again, multiple zones of, in this case, panel radiators. But remember, this could be multiple zones of radiant panel heating, or it could be a combination of panel heating, panel radiators, maybe even a fan coil. So the home run approach is a very flexible approach in terms of combinations of heat emitters. This circulator can adjust its speed based on what the fluid demand is out here. And in this case, I'm showing an electric boiler simply piped in parallel with the heat pump as a booster or as a backup. So if the heat pump capacity is insufficient on a very cold winter day, the electric boiler can come on. Again, some heat pumps have internal controls that can automatically provide a contact closure to signal the auxiliary boiler to come on. Okay. Same system, the only difference being now fossil fuel boiler. This could be natural gas, propane, fuel oil. Very important detail. If we're going to operate this system at low water temperatures, if we're using outdoor reset control, or maybe we're adding insulation to the building to bring down the supply water temperature, or maybe we're adding heat emitters to also bring down supply water temperature. If this is a conventional boiler, it's not designed to operate with sustained flue gas condensation. And we could potentially, especially in a retrofit situation, have a boiler that for years has operated well above dew point. So it has not experienced sustained flue gas condensation. And all of a sudden we've created a modified system that may force that boiler to operate at conditions that would cause sustained flue gas condensation. So you want some type of a protection valve, a mixing valve in there. One option is Caleffi does make a valve called Thermal Protect, and it's simply a thermostatic high flow capacity three-way valve. And what this will do is, as this boiler is warming up, it will simply recirculate the fluid. So it allows that boiler to come up to temperature quickly because, in effect, it's disconnected it from any load other than just maybe 2 or 3 gallons of fluid here in this piping. And once this sensing element senses that the return temperature is high enough, it'll start opening the cold port and closing this bypass port. And now we're allowing some of that flow to go out. So again, I know it's a seminar or a webinar rather based on cooling, but I do want to mention, as you build these systems that are multi-mode or multi-load, be careful about protecting conventional boilers against sustained flue gas condensation. Here's another variation. The difference here is, instead of using a tank with internal coils, we're using I'll call it a tankless, or I'm sorry, a coilless tank, and we're using an external stainless steel heat exchanger as our domestic hot water, either preheater or perhaps even a full heater, depending on the temperature of this tank. There's a flow switch here. This determines whenever you draw domestic hot water and the flow gets above roughly about 0.7 of a gallon per minute. This switch would sense that. It's going to turn on this circulator. We're drawing warm water from the top of the buffer tank down through primary side of the heat exchanger and putting it right back in. And our cold domestic water is going up in counterflow and getting heat. How much heat does it get? You got to do the calculations on this. The size of the heat exchanger will certainly matter, as well as what the flow rate is, what the temperature of the buffer tank is. But there's online software to help you with that. Here's a system. This is actually one we talked about in Coffee with Caleffi back, I believe it was in February. This is a system that brings together 10 panel radiators, 2 zones of floor heating, and these are all relatively small room by room zones, variable speed circulator, reverse indirect, electric boilers backup. Here's our monoblock heat pump, and then our diverting valve that goes out to our cooling coil. And we're also tying a heat recovery ventilator into the return side of the air handler, so we can provide fresh air. So we're doing 4 things with this system. We're doing space heating, cooling, domestic water heating, and heat recovery ventilation. And I really feel that is a great offering for today's new construction in particular. We're building houses much tighter from an air leakage standpoint. Ventilation, indoor air quality is becoming a very significant decision maker in some of these cases, or significant consideration. So why not extend your offering from providing just space heating and perhaps cooling to also include domestic water heating and heat recovery ventilation? Okay. And actually there's a YouTube, you can pick up that link right there. Just go back to the Caleffi YouTube channel. And as I said, we did a Coffee with Caleffi earlier this year covering that system. And let's see, just in the interest of time, I'll show you a few details. Here's the 3-way valve. The heat pump that was used in this system had a fairly high pressure drop characteristic. So this is a Taco 2400 circulator. That's a fairly powerful circulator, but that circulator in cooling mode has to not only provide flow through the heat pump, but also has to take into account the head loss of the piping and the coil out here in the air handler. Here's that B&D air handler that was used to provide the chill water cooling. Okay. Here are those whole right clips that we looked at earlier. Again, if you'd like the PDF of the presentation today, Max can get that out to you. For airflow, what we did is we used supply air within the attic trusses. The attic trusses were all within the thermal envelope of the building. We used spray foam insulation against the underside of the roof deck. So we were able to easily provide supply air through ceiling diffusers to all the spaces in the building. And then rather than create an entire return air duct system, we use these in the doors. These are a product from Tamarack Technologies. And basically what they are, you cut the bottom of the interior doors, you slide this up, and there's a couple screws that hold it in place. This provides light separation and acoustic separation, but it allows air to flow through there. So I should say it suppresses, especially acoustically, it suppresses acoustic transfer, it suppresses light transfer, but if the door of that room is closed, it allows air to come through without building a substantial back pressure on the system. So all the interior doors have these, and all the return air comes back to a single return air grill, a filter grill. The filter is accessible right from the ceiling in the hallway where this grill is located, and then the HRV ties directly into that. Again, I'll point you back to Hydronic 13 for more configurations that involve both air-to-water and water-to-water heat pumps with multi-zone heating, multi-zone cooling, just some schematics and reference information. Okay, I just took a couple examples of what is in Hydronic 13. It's available on the Caleffi site. It's www.hydronics.caleffi.com. And you'll see a whole listing of PDF files for the different issues. And real quickly, I just want to show you another market opportunity, both from the heating and the cooling standpoint. And there's a lot of small commercial buildings with slab on grade construction. Many of the new ones are using floor heating. Floor heating has finally, established such credibility that in garages or shops or fire stations, it's getting a lot of specification. So there's a lot of buildings in this category, and it can be a very simple system where an air-to-water heat pump, in this case a monoblock, goes through a hydraulic separator and then out to floor heating. And the reason a hydraulic separator is in there is to allow constant circulation in the floor circuits, which I'd like to do in garage type facilities because it helps get rid of the cold spots right here, right inside these large overhead doors, okay? So you can do constant circulation over here and just simply have the heat pump turn on and off or modulate to control the supply water temperature going to the floor. You can do that with outdoor reset control. That will keep the heat pump operating at the lowest temperature that will still adequately heat the building. The lower you can keep that temperature, the higher the COP of the heat pump is going to be. Real quickly, I expanded it to 2 heat pumps here in a commercial facility. If you have single phase power, you might need 2 based on heating capacity. And then finally, if they're doing the air to water heat pump primarily for heating, why not add cooling into the mix? It could be very simple. It could be as simple as 2 manual valves that you change to change the distribution side from heating to cooling or vice versa, or some type of electrically operated diverter valve, but a suspended air handler with minimal ducting. Think about some of these shops. I mean, we've been in facilities over the years in my area that simply don't have any cooling. And on these really hot days, I mean, they have fans going, but it's very hot in here. So as part of bringing an air to water heat pump into that picture, we can add cooling at a relatively low cost, and that could be a game changer on that in these types of decisions. And then I'm done. I'm going to turn it back over to Max. I know we're very close to 2:30 here, but if we do have a few extra minutes, let's do some questions.
Sounds good. And then if you have any specific questions, you're welcome to give us a call and talk to a live person on the tech support line, or that email account on the screen there is monitored by our whole team there too. So if there's something specific you want to talk about afterwards, and we didn't get to all the questions, I tried to answer quite a few of them as we were going, but we'll get back to some people. Tag us on social media. We love to see your projects out there. We love to show these systems when they're in practice, because a lot of the questions got into specifics about, well, what about this scenario? What if it's really cold? What if it's really humid? There is, I would say, within the group of our hydronics manuals, something for everybody there. I think for the extreme cold climates, or even the scenarios that, as somebody mentioned, heat pump water heater might be a good way to go. Huge domestic load, but maybe not the extremes on the space heating side, or whatever the case may be. So I think as a group, we've got pretty good answers to those questions. One of the things that comes up when we do any webinar about hydronic cooling is dew point. We had a lot of those questions, and you did a great job going through those considerations there. One other recommendation I would make is apply ASHRAE standards 55 and 62.1 or 0.2, depending on the project, even if you're not required to. That kind of gives you the temperature and humidity boundaries that are going to help with these designs. If you need some sort of, we had some question about, well, what if I need 33-degree chilled water to make this happen? That might not be, we might need to look at some other things there. That's going to break some of those rules that Caleffi didn't establish, but are just temperature, humidity boundaries that we should be aware of. What else would you recommend along those lines, John? Mostly I'm saying don't be scared of it. We can avoid the dew point. We just have to look at the capacities that are.
Yeah. Dew point, it's critically important with any type of radiant cooling. And in looking at the pre-submitted questions, I know there were several dealing with radiant cooling. Radiant cooling works, it can be done. It's primarily at this point in time used in commercial buildings, especially buildings that have very strong sensible heat gain. And a good example would be an airport terminal where you've got skylights or just large windows. You have a lot of solar heat gain. You've got heat gain from people and lights, where a radiant floor can absorb a lot of that. If you're just thinking about getting into small scale hydronic cooling, I would encourage you to start with an air handler or multi-zone consoles rather than radiant. And I don't do that to downplay that radiant cooling works. It can work well. but I would rather see you gain your experience with a relatively simple system, especially if you could do a single zone chill water air handler, learn the piping insulation details, learn the cooling loads and how to put these systems together. And eventually we may want to expand out into radiant cooling, but I use the term walk before you run. Start off with some type of an air handler. And I'd recommend a single zone system in a residential system to start with and experience it. We've done several. I've been very pleased with how they've operated. My biggest fear, quite honestly, as small scale chilled water starts to become more and more used, is that installers will not insulate piping correctly. That is going to be a downfall. So I try to stress, and I'll stress again, if you're going to work with any type of chill water cooling system, it is important to do the piping insulation completely and properly, and not create these situations where condensate is dripping on surfaces and causing corrosion and so forth.
That's great. I think that's probably a good spot to end it. There are still a handful of questions that are a little bit more complex, and we'll get back to everybody there. But I wanted to thank you, John, for presenting again today. I think it's just important to show the different ways that these systems can go together. There's no cookie cutter with this, but the energy efficiency opportunity there is so enormous. So thanks again. We'll see you next month. I put the link for next month's Coffee with Caleffi in the chat there if you want to sign up and come back to hear more about glycol. We'll see you soon. Thank you.
Thanks, Max.